Hey everyone, welcome to the final episode of this series. Build a neural network in C++ from scratch for robot collision prediction. It's been an amazing journey. We started from the very basics, building everything from scratch. The matrix class, activation functions, layers, training logic, and even how to load and process our dataset. And today, we're going to use all the libraries we have built and see how we can create a neural network and train it. So let's get started. This is our main file, the one we'll actually run. And first of all, we need to include all the necessary libraries. And here's the first one. Hash include iostream, hash include vector, and hash include iomanip, hash include std accept, hash include layer.hpp, hash include neural network.hpp, and hash include csv loader.hpp, hash include log.hpp, and the last one, hash include sstream. These headers bring in everything we have built so far. I've already explained each of them in the previous episodes, so let's just continue. And next, I'll add using namespace std. This just lets us use the standard library features without writing std::: every time. It keeps the code clean and readable. And now, let's create our main function. Int main. To make our program more reliable, I'll wrap the main code inside the try block. Try and catch, and inside parentheses, const exception reference e. And here we print out an error message, CERR, error, colon, e.what, and int l. And then return 1. This catch block will handle any runtime errors and print a clear message to the console so we know exactly what went wrong. Inside the try block, the first thing we'll do is create a vector of layers. This will define the architecture of our neural network. Vector, layer, layers. Now we'll define the layers of our neural network. Each layer needs an ID, the number of neurons, and the activation function. And we just have 3 layers, and here they are. Layers dot in place underscore back, and we pass in 0, 24, activation type, none. And layers dot in place underscore back, we pass in 1, 12, activation type, ReLU. Layers dot in place underscore back, 2, 1, activation type, sigmoid. Let me explain each layer briefly. Input layer, 24 neurons to match the 24 sensor readings from our dataset. No activation function is needed here. And we have one hidden layer, 12 neurons with ReLU activation. And output layer, 1 neuron with sigmoid activation. And remember, this is just one possible architecture. You can experiment with your own number of layers and neurons. If you find a combination that gives better results, share it in the comments. I'd love to see what you come up with. Next, we create our neural network object using these layers. Neural network, and I'm gonna call it NN, and we pass in layers. Next, we need to create containers to hold our training and test data. This includes the sensor readings, the expected outputs, and the row IDs to keep track of each data point. And here's the containers. Before we load the data, we'll create a string variable to store the user's choice about loading a previously saved model. String load_model. We'll see how we use it in a moment. Now, let's load our sensor dataset from the CSV file and split it into training and test sets. If CSV load and split sensor data, and we pass in the CSV file name sensor_readings_24.csv, and training_features, training_labels, training_IDs, test_features, test_labels, test_IDs, and 0.8. This means 80% of the data will be used for training and 20% for testing. If the function returns true, the data has been successfully loaded and split. Otherwise, we print an error message and stop the program to prevent errors later. And here we say else CERR failed to load sensor data and /n. Then we return 1. Once the dataset is loaded, we'll ask the user whether they want to load a previously saved model or train a new one from scratch. Cout, do you want to load the model? And inside parentheses, y/n and colon. Then cn load_model. Then we check if the user enters y, we load the existing model. If load_model is equal to y, or load_model is equal to capital Y, cout loading the model /n and nn.load model. We can pass in the model file name, but we don't need to do that here. If we choose not to load, here we say else load_model equals n and nn.train, and we pass in training_features, training_labels, and the learning rate is 0.029 for 1300 epochs, and the batch size is 8. Now that our neural network is ready, let's print and log its performance on the test dataset. We'll loop through each test row, make a prediction, and display it alongside the actual value. First, let's have a header to separate the prediction section in the console and log file. And here's the header. And then we loop through the test features. For size_t, I equals 0, I less than, test_features.size, and ++i. Now we need a string stream to neatly format the data we want to print and log. String stream, and we call it data. Next, we'll start formatting our output. we have the prediction header, the row ID, and the sensor data itself. This is the header, and then data, row ID, colon, test underscore IDs, square brackets, I, and slash n. And next one is sensor data. Data, sensor, data, colon, and then for double val colon test underscore features square brackets I data fixed set precision, and we pass in 2. Then we have val, and after the loop I want to have an slash n, data slash n. Then we'll make a prediction for each test sample, display the predicted value alongside the actual one, and also log everything. Let's do it. Vector double prediction equals nn dot predict, and we pass in test underscore features square bracket I, data prediction colon fixed set precision, and we pass in 4 and prediction square bracket 0 slash n. Next we have the actual value, data actual colon test underscore labels square bracket I square bracket 0 and slash n. And finally we're going to print and log the data. Cout data.str and L scope log, we pass in data.str. To evaluate our neural network's performance, we'll calculate a confusion matrix, a simple table that helps us understand how well our model is performing. It shows how many predictions were correct and where the model got confused between the classes. In a confusion matrix, we have these 4 key metrics or counters. True positives, predicted collision and collision happened. True negatives, predicted no collision and no collision happened. False positives, predicted collision but no collision happened. False negatives, predicted no collision but collision happened. Let's define and initialize all these counters to 0. Int tp equals 0, tn equals 0, fp equals 0, fn equals 0. Next, we'll loop through each test sample to compare the model's prediction with the actual value and update our confusion matrix counters. For size underscore t I equals 0, I less than test underscore features dot size, and plus plus I. For each test sample, we use our neural network to make a prediction, and here we say double pred equals nn dot predict, and we pass in test underscore features square bracket I and square bracket 0. Since this method returns a vector, we take the first element as the predicted value. Because our network outputs a probability between 0 and 1, we'll convert it into a binary prediction, collision 1 or no collision 0, using a simple threshold like this. Int predicted equals pred greater than or equals 0.5, this is the threshold, question mark 1:0, And then we get the actual label from our test dataset. Since the labels are stored as doubles, we cast it to an integer so we can compare it with our binary prediction. Int actual equals static underscore cast int inside parentheses test underscore labels square brackets I square brackets 0. Finally, we update the confusion matrix counters based on the comparison between the predicted and actual values. If predicted is equal to 1 and actual is equal to 1, TP++. Else if predicted is equal to 0 and actual is equal to 0, TN++. And else if predicted is equal to 1 and actual is equal to 0, FP++. Else if predicted is equal to 0 and actual is equal to 1, Fn++. Once we have our confusion matrix counters, we can calculate some key performance metrics for our neural network: accuracy, precision, recall, and F1 score. We're going to start by adding all the counters together. Int total equals TP plus TN plus FP and plus Fn. And then we calculate the accuracy. Double accuracy equals static underscore cast double inside parentheses TP plus TN divided by total. This is the percentage of correct predictions out of all predictions. And next one is precision. Double precision equals inside parentheses TP plus FP is equal to 0 question mark 0.0 static underscore cast double TP divided by TP plus FP. Precision means of all predicted collisions, how many were actually collisions. Now let's calculate recall. Double recall equals TP plus Fn is equal to 0 question mark 0.0 colon static underscore cast double TP divided by TP plus Fn. And this one means of all actual collisions, how many did we correctly predict? And the last matrix is double F1 underscore score equals inside parentheses precision plus recall is equal to 0 question mark 0.0 colon 2.0 times precision times recall divided by precision plus recall. F1 score is the harmonic mean of precision and recall, a single number that balances both. These metrics give us a complete picture of how well our model performs on the test data. Now we print and lock our confusion matrix and metrics like this. Finally, if we just trained a new model and didn't load an existing one, we can ask the user whether they want to save it for later use. And here we say if load underscore model equals to n string save underscore model cout Do you want to save the new model inside parentheses y/n and colon, and cn save underscore model, and then we say if save underscore model equals to y, or save underscore model equals to capital Y, then cout saving the model, and nn.save model, else cout model not saved. And at the end of the main function, we have return 0. Now that everything is set up, let's run the program and train our neural network. Here, we can see the class balance information and how we split our dataset. This tells us that our dataset is slightly imbalanced, with more collision samples than no collision samples. Then we have the training settings. As you can see, the training has already started. The binary cross-entropy BCE loss is gradually decreasing, which means our network is learning and improving with each epoch. Once the training reaches 100%, we'll see the duration of training, how long it took, and then we'll see how well the network performs on the test dataset. And here's the result. Let's see. Look at these results. Our neural network achieved over 94% accuracy, with precision and recall both around 95%. That's incredible, especially considering the sensor data is quite noisy and our dataset isn't perfectly balanced. Despite these challenges, the model learned to predict collisions almost perfectly. Seeing the confusion matrix, only 34 false positives and 26 false negatives out of 1092 test samples really shows the power of training a neural network from scratch. This is exactly why building a neural network yourself is so rewarding. You understand every step and then you get to see it work on real-world data. And this marks the end of our robot collision prediction series. If you have followed along from episode 1, you now have a deep understanding of how neural networks work under the hood, from the math to the C++ implementation. Stay tuned. I'll be back with a new series on building neural networks from scratch in C++. We'll explore different algorithms, optimization techniques, and loss functions. Make sure to like this video, subscribe, and share the series if it helped you learn something new. Your support keeps this kind of content coming. You can download all the files from GitHub. The link is in the description. Thanks for watching.